All right, so now that we've defined the integral and we've kind of talked about what it stands for, we're going to do the actual calculation of the definite integral. So we had some practice in the last lesson setting up those Riemann sums. And so now we're going to actually go through the whole process of plugging in the formulas from the sigmas so that we can actually take the limit. So let's write down our process, our steps first, and then we will do it. Okay, so the first few steps we've already done, which is we need to create the sum itself. And so we need to find expressions for, remember we needed delta x, b minus a over n. Well, we might as well just write that in. Right. The x sub I star, and I suggest you have a choice. So I would just use the, is that the right hand endpoint that doesn't have the I minus one. Okay. And then of course we need to plug those x sub I star expression into the function itself. And then once we do that, we use these that we just found, expressions, to write a limit of a Riemann sum. So these are the two steps that we have already done. But now we need to evaluate that limit. And so in order to do that, we need to get rid of the sigma parts. So we're going to start by simplifying. And then we're going to put it in closed form, which remember means it does not have the sigma anymore. And we'll be doing that using the formulas. There were formulas for, remember the sum of I, the sum of I squared, etc., a constant, all of those formulas. And then once we simplify that, we're going to take the limit as n goes to infinity. Okay, so let's do one. Well, we're going to evaluate this integral from 3 to 8 of 6 plus 2x. Okay. All right, so I need to write down what my delta x is, which is b minus a over n. So 8 minus 3 in this case over n. Then I'm going to do my x sub I star, which is a plus I delta x. So my a is 3. My delta x is 5 over n. So it will be 3 plus 5i over n. And then I need to plug that into the function 6 plus 2x. So it'll be 6 plus 2 times x, which is represented by 3 plus 5i over n. Yes, 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 you need to simplify. These problems are going to get really tedious if you don't. So I've got 12 plus 10i over n. So there's the pieces I need. And now we're going to set up the actual limit. So this integral will be equal to the limit as n goes to infinity of the sum, I goes from 1 to n, of delta x, 5 over n, times f of x sub I star, which is 12 plus 10i over n. So that is that first step of just plugging in the pieces to the limit form. Now, we need to simplify this a little bit, which means we're going to distribute. That'll be 60 over n plus 50i over n squared. And in fact, you know what? Why don't I, in this step, go ahead and just break it into the sum like this. Okay. It's the limit of this whole thing, and I'm now starting to break up my sum. Now, remember what we talked about. The thing inside of these that we treat as a variable is the I, and n is like a constant. So this is really just a constant. And this would be 50 over n squared times the sum of I. So you don't have to factor the constant out. We did have a formula that said you just multiply the constant by n. But if it makes it easier for you, I'm going to factor out both of these constants. So my next step is going to be to get rid of these sigmas and use what the sum from I equals 1 to n of a constant is, which is that constant times n, and the sum from I equals 1 to n of I, which was n times n plus 1 over 2. So that is my next step. I'm leaving everything else the same. And I'm just substituting in the formulas so that I can get rid of the sigmas. So now we're going to do some simplifying. I can cancel some n's. I can reduce this number here. So I'm looking at the limit as n goes to infinity of 60 plus 25 n plus 1 over n. I'm just kind of putting the n's together because when we're finding a limit as n goes to infinity, do you remember, and this is one of the reasons why we spent some time talking about this in this lesson, if I have a rational function, I can determine the limit by looking at the powers on the top and the bottom. So that's why I kind of wrote this together. And if they're the same, which they are in this case, then the limit is just going to be the coefficient of the highest power over the coefficient of the highest power. So that means that this whole piece right here approaches 1. Another way to see that is you could have written it as 25 plus 25 over n. This part would go to 0 because it's still got an n in the denominator, and this part would just go to 25. If this whole thing here goes to 1 times 25, it will go to 25. So it works out the same. So as I apply my limit, I have a limit of a constant plus this constant times 1. So it'll be 60 plus 25, which is 85. Okay. That was fun, wasn't it? Well, I have good news for you. There's another one here for you to try. Yep, I know. Pause the video and see what you can make of it. Okay, I've done a lot of the groundwork here. So again, you might want to just press pause. I'm not going to talk through every single piece of this because it's the same thing that we did before. I calculated all of my pieces. When I got to plugging in the x sub I star, and I have this, I need to simplify this because I don't have a way to get out of my sigma notation unless I have individual terms. So I squared this, I distributed the 4, and then I combine all my like terms to get the most simplified version of f of x sub I star I could. I plugged that into the limit. And then in this step, I'm just distributing my 3 over n, breaking it up, and then I'm substituting in my formulas for I squared, I, and a constant, simplifying. So I've gotten down to this point where I've plugged everything in and I've simplified. And again, you can see I've written the constant in front and then the n rational expression next to it. So I'm looking at these for my limits. As n goes to infinity, if the top degree and the bottom degree are the same, which they are here, right? Because if I FOIL this out, this will be 2n squared as my highest power over n squared. So this part will go to 2. And this one is n plus 1 over n, so it will go to 1. So in my last step, I have, oh, I don't need my limit anymore. Silly me. I need my 9/2 times that limit, which was 2. Minus my 9 times that limit, which was 1, minus 3. And so it looks like my final answer will be minus 3. Okay. And one last thing that we want to talk about here are some properties of definite integrals. These are just things that you're going to need as you move forward with calculating definite integrals. So first one is, if you're taking the integral of a constant, what's that going to equal? Well, let's think about it. If I have a constant function, this is C, and I'm cutting it off between A and B, what is this area? It's a rectangle, and its area will just be C as the height and B minus A as the width. So it's just going to be C times B minus A. All right, next property, if I have an integrand that has a constant in it, I can pull that constant out front and multiply it by the integral. It's based on a limit, and that's what we're doing with limits. Same with adding and subtracting. If you're doing the integral of a sum or a difference, you can do the two integrals separately and then add or subtract them. And then last but not least, this one, if we're doing an integral from A to B, and we have some number C that's inside that interval, right? It's in the interval from A to B. Then you can actually break it up into two integrals from A to C and C to B and just add those together. So for a visual on that one, let's say my function looks like this. And here's my A and my B. And then somewhere in between there is a C. So the idea is, if you do this integral, A to C, which I've labeled with 1, and then C to B, which I'll label with 2, it's exactly the same thing as going all the way from A to B. You'll catch this whole region. Okay, and those are your properties of integrals, which you'll be using a lot of in Calc 2.